Amplitude and loudness. We all know that we measure amplitude in decibels. And a reminder that a decibel is dimensionless. We measure distance in feet or meters or inches, but we measure decibels without any dimensions at all, and that's because these are comparisons between values with the same units. Decibels compare to amplitudes. If we're talking about sound, we're measuring sound pressure level in decibels. We're comparing the level of one sound to a reference level of sound. When the audio becomes an electrical signal, we still measure the amplitudes in decibels, but this time our reference is power, or more commonly, voltage. Humans hear differences in sound pressure levels. In fact, we hear a wide range of differences, all the way from 0 dB of sound pressure level up to the threshold of pain, 120 decibels. We measure this difference on a logarithmic scale. The reason for the logarithmic scale is so that we can capture this wide range of values, all the way from 20 micropascals up to 20 billion micropascals, quite a wide range of difference. If we double our pressure, let's say from 1,000 micropascals up to 2,000 micropascals, we increase our level by 3 decibels, 3 dB. We say that the range of human hearing is the dynamic range, which is the difference between the loudest sound a voice can make and the softest sound the same voice can make. In audio equipment, we also measure amplitude with decibels, but here we are comparing decibels to either voltage or to power. Way back in the old days, when there used to be vacuum tubes, the 0 dB reference was 1 milliwatt of power, which happened to be 1 milliwatt dissipated across 600 ohms of resistance, and this was called the dBm. Well, when vacuum tubes went away and transistors and integrated circuits started replacing electronics, the experts found a new reference, initially the dBu, or dB(v), which kept the same reference voltage as the dBm, 0.775 volts, but this time they didn't compare it to any resistance values. It wasn't long before the experts decided a better reference was more appropriate for modern equipment, and this became the dBv, capital V, which now sets the reference level of 0 dB at 1 volt. To summarize reference levels, in the acoustic world, we set our reference at 0 dB of sound pressure level, and when the audio becomes an electrical signal, our reference becomes voltage or power. We found that there is no direct relationship between frequency and amplitude. That is to say, in the physical world, as amplitude changes, it doesn't affect a change in frequency, and versa vice. If frequency changes, it doesn't mean that amplitude changes. However, as humans, we do perceive a difference between loudness and pitch. It turns out that, surprise of surprises, that humans hear voice frequencies better than they do lower frequencies or higher frequencies. Which is to say, as frequencies change from the mid-range to higher or lower frequencies, we humans hear them less well. And to make things really interesting, when the amplitudes are lower, we perceive these differences even greater. Conversely, as the amplitudes of audio get higher, this difference becomes less apparent. If we reproduce all the audio frequencies from 20 to 20,000 at the same level as shown in the red line, our hearing responds less well to the low frequencies and the higher frequencies as shown on the blue line. Notice that at 1 kilohertz, we hear the exact frequency. However, when the frequency changes to 100 hertz, we hear that 100 hertz as though it were less loud than it actually is. Again, the interesting part is that if all the audio levels are low, this difference becomes more pronounced. As the audio levels increase, this difference becomes less apparent. Well, some brilliant scientists and engineers in the past tried to measure this difference, and they introduced the Phon.
Sunday, Monday, happy days. Tuesday,
No, not the Phons. The Phon. P-H-O-N. Now, the Phon is actually a measurement of loudness, whereas we measure amplitude in decibels, we measure loudness in Phons. Confusing, huh? Remember that amplitude measures a physical reality. Phon's loudness just measures our psychological perception of the amplitude. We saw that at 1,000 hertz compared to the other frequencies, our ear hears exactly what's reproduced. So by definition, we define 1 decibel to be equal to 1 fon. Let's take a look at fons graphically. Here we see our frequency and our amplitude coordinates. We know that at 1 kilohertz, the number of fons we hear is exactly equal to the amplitude in decibels. So 20 decibels is equal to 20 fons, and 40 decibels is equal to 40 fons. This is by definition. So the way this scale was developed was by having people listen to other frequencies at the same amplitude. When subjects listened to 100 hertz at 20 dB, they perceived it as being much lower than the 1,000 hertz and were asked to turn up the volume of the 100 hertz until it sounded just as loud as the 1,000 hertz. So the loudness of 100 hertz at 20 decibels translates into 40 fons, or a difference of 20 decibels. Using the same techniques at higher amplitudes, this time the subjects were asked to listen to 1,000 hertz at 100 decibels, pretty loud, and compare that to 100 hertz at 100 decibels. Again, they increased the amplitude of the 100 hertz until it sounded just as loud as the 1,000 hertz. But this time, the increase was only 2 or 3 decibels instead of 20 dB. Repeating this technique for all frequencies and different levels, a set of curves is generated known as the equal loudness curves, which is a subjective measure of human perception of loudness. As a demonstration, here's an example of 1,000 hertz at 80 decibels. Compare that to 100 hertz, also at 80 decibels, and to 10,000 hertz, also at 80 decibels. The 110,000 hertz sound softer than the 1,000 hertz. This completes Module 3, Human Hearing, Amplitude and Frequency. But before we continue, I'd like you to consider, can you name the units that are used to measure frequency, amplitude, and loudness? What amplitude is being measured in the physical world, and what amplitude are we measuring in the electrical world? Finally, can you describe the equal loudness principle? If so, in Module 4, we'll investigate how sound behaves in a room and consideration for what makes a room sound good. Talk to you then.